Hi guys, welcome to your 12-6 notes on permutations and combinations. By the end of the day, you will be able to find permutations and combinations. The key idea of this lesson is that you can use counting methods, ways to count things, to find the number of possible ways to choose objects, either with order or without order. Let's start with this example. You're at a bonfire at the beach, and you have the following options to make s'mores. You can use honey graham crackers, you can use cinnamon graham crackers, my personal favorite, or you can use chocolate graham crackers. You have the option of making your s'more with 1 marshmallow or 2 marshmallows, and finally you can put regular chocolate on it, or you can put chocolate that has peanut butter in it on your s'mores. So given these options, how many different kinds of s'mores can you make? There are 2 ways to figure this out. The first way, for those of you who like visuals, is we can draw what's called a tree diagram. Now with a tree diagram, you'll start with your first set of options. That's your graham cracker. So you say, okay, if I have a honey graham cracker, or a cinnamon graham cracker, or let's say I pick a chocolate graham cracker. A chocolate graham cracker. Those are your first options. And then say, after you pick your graham cracker, you decide marshmallows. So you can have honey with 1 marshmallow or honey with 2 marshmallows. You can have cinnamon with 1 marshmallow or cinnamon with 2 marshmallows. And finally, you can have a chocolate graham cracker with 1 marshmallow or a chocolate graham cracker with 2 marshmallows. So we started out having 3 possibilities. Now we have 6. And then finally, we decide, do we want regular chocolate or do we want peanut butter chocolate? So if we have honey with 1, we can have regular, or we can have peanut butter chocolate. We take that same process, honey with 2 marshmallows, regular chocolate, or peanut butter. And then again, cinnamon with 1 with regular peanut butter, 2 regular peanut butter, and finally, chocolate with 1 marshmallow, regular peanut butter, and chocolate with 2 marshmallows, regular or peanut butter. So this is what a tree diagram looks like. Now, a tree diagram can take a lot of time. I mean, it's really cool because you can see the different possibilities. Like if I start with honey, this is what I'll get. Or if I have cinnamon graham crackers, then these are my options. Or if I get chocolate graham crackers, these are my options, right? All these different possible combinations. However, like I was saying earlier, it can take a lot of time and it can take a lot of space. So we have another method that we can use. This is called the multiplication counting principle. The multiplication counting principle is a shortcut, and it says if there are m ways to make a first selection and n ways to make a second selection, let's pick a different green, and n ways to make a second selection, then to find your total options, that's m times n. That's why it's multiplication, because you multiply. And in counting, we're counting all the different options. It's a principle because it's an idea. So if you have m first options and n second options, then you have m times n total options. For example, if you start out with 9 shirts and you have 4 pairs of pants, and we're going to assume that they all go together, then that's a total combinations of 9 times 4, which is 36 total possible outfits. And it's not limited to just 2 selections. You can use it as many options as you want. For example, we go back up here. We have 3 types of graham crackers, and we have 2 options for marshmallows, and we have 2 options for chocolate. I spelled chocolate wrong. chocolate. Then, according to the multiplication counting principle, all we have to do to count all these options up is multiply across. So 3 times 2 is 6 times 2 gives us 12 total options. And if we looked up here at our tree diagram, we counted all those options. That gives us our first option here is honey with 1 marshmallow and regular chocolate. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options again. So no matter which way we do, we get the same kind of answer. We have 12 possible different kinds of s'mores. Cool. Now what if it gets a little bit more complicated? Well, if it gets a little bit more complicated, then we're going to need a brand new tool. And this is, guys, this next concept that I'm about to teach you shows up a lot in math jokes. In fact, if you go on Reddit, there's an entire subreddit devoted to unexpected factorials. So that's great. So the punchline to a lot of math jokes is something called a factorial. Now, a factorial looks like this. It looks like n with an exclamation point like that. So you go, n! I'm just kidding. That's not how you pronounce that. You pronounce this not as saying n, but by saying n factorial. Okay, don't shout it. I mean, of course shout it, it's fun. But anyway, for any integer n factorial, or n, is the product of all the integers from n down to 1. And that is fancy math language for you start with n, and then you multiply times n minus 1, and then you multiply times n minus 2, and then you multiply by all the numbers times 3 times 2 times 1. That's it. Now it's a bit abstract, so let's do a bunch of examples. For example, 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And then we say that 0 factorial, we just define it. We say, oh, that's 1. So if you ever get 0 factorial is 1. Cool. So factorial is multiplying from that number all the way down to 1. Now factorials show up in what's called a permutation. A permutation is a way to arrange objects in a specific order. For example, if you have these 3 letters, A, B, and C, we are looking for all the possible ways to arrange the letters A, B, and C without repeating any letters. So you have, A, B, C, then you have A, C, B, and B, A, C, B, C, A, C, A, B, C, B, A. Is that it? I think that's it. Yeah. So there are 6 possible permutations. Going back to our intro activity, you can think of it as, well, we have 3 spots, and in our first spot, you can either have A, B, or C. And then depending on what you get, let's say we pick A first, then we can do B or C, so there's 2 options left. And then depending on that, there's really only 1 option. If we pick B, there's only 1 option left. So that gives us 3 times 2 times 1, which is 6. That's where that comes from. You can also think of permutations like a race. If you have a race, then the order matters. It matters who gets first place, who gets second place, and who gets third place. For example, if Mia and Brayden and Ariana went racing, if Mia came in first place and then Brayden and then Ariana, that would be different than if Brayden won first place and then Ariana and Mia came last. So here our order matters. Your order, oh, that's super important. Your order matters. We'll write that down later. Let's look at a baseball lineup, talking about Brayden. So a baseball lineup has 9 positions. How many different batting orders can you have with 9 players? Well, let's look at it. So we have 9 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Make a little bit of space. So if we pick our first person to go, really we have 9. We have 9 possible choices for our first batter. And then once we pick him, there's 8 people left who could go second. And once we pick him, we have 7 people left who could be third. And then there are 6 possible choices for our fourth batter. 5, and then 4, and then 3, and then 2. And then once we have the first 8 people set, we've only got 1 more person, right? So there's really only 1 more option. Now, according to what we learned earlier, to find out how many options we have, we just multiply across. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and that's equal to 9 factorial. Cool. But also we can multiply that out, right? 9 times 8 is 72 times 7 times 6, which is 42, times 5 times 4, which is 20, times 6. We do all that all together. That gives us 362,880. That's a lot. That's the worst circle ever, right? That's a lot of possible combinations. So there you go. Oh, I shouldn't say combination because it's not a combination. It is a permutation because here order matters. We are arranging objects. Fun, right? Now that's if we had 9 people and we used all 9 people. It gets a little bit more complicated when we don't use everyone. To find what that is, we're going to use what is called permutation notation. Permutation notation looks like this. We start it with a P for permute, right? It's a permutation. And we say, okay, if we have n things and we want to pick r of them to arrange, so it's a little n, big P, little r, represents the number of permutations of n objects arranged r at a time. Now the key word here is arranged. The arranged tells us that order matters. Okay? Just like in the race, it depends on who comes in first place, second, or third. And to calculate NPR, that's equal to n factorial divided by n minus r in parentheses factorial. That's one of our key ideas of the day. So you will want to memorize this, put it on a note card, love it forever. To find a permutation of n objects, to find a permutation of r objects from n objects, that's n pick r n factorial over n minus r factorial. For example, let's say that on our baseball team, we no longer have 9 players, but instead we have 13 players. That means 4 people won't be included in our lineup. Okay, so that will give us 13, or rather here, different batting orders. Batting order means we want to pick 9 people, so 9 is going to be our R, and then N is our total, so 13 is going to be our N. So that means N pick R is 13 pick 9, which is 13 factorial all over 13 minus 9 factorial. Plugging that in, that's 13 factorial divided by 13 minus 9 is 4 factorial. Now I know it looks very excited, like someone's super excited about math. 13 minus 9, 13, 4, yay, cool. But this factorial, this means something, remember? 13 factorial equals 13 times 12 times 11 all the way down. I can't write that fast. All the way down to 4 times 3 times 2 times 1. And then 4 factorial is 4 times 3 times 2 times 1. Wow, that's a lot of math to do. It's a lot of computation to do. The good news is that this 4 times 3 times 1, that'll reduce out with the 4 times 3 times 2 times 1. Yeah, all on top. So that gives us just 13 times blah, 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 times 5. When you take out your handy-dandy calculator, that gives you 259,459,200 possible batting orders. That's a lot of options. In fact, that's 715 times as many as if you just had 9. So that's a lot. Just adding 4 players gave you over 700 times as many options. So again, there are so many different ways here because order matters. That's the key, most important thing to note here. Order matters when you use a permutation. What if order doesn't matter? Great question. If order doesn't matter, then we use what's called a combination because it will combine them. A combination is a way to arrange objects with no specific order, where order doesn't matter, in no specific order. For example, if we're looking at the letters A, B, and C, then A, B, C, that's the same thing as B, A, C, which is the same thing as C, A, B, because those are considered the same thing because they all use the same letters, right? It's the same group. Here, order doesn't matter. It's like, to revisit our race example, instead of looking at first place, second place, or third place, you just want to know, okay, what are like the top 3 without knowing, first place, second place, or third place. We don't care about that. It's like if you had a basket and you just want to pick 3 things to put in your basket, but the order doesn't matter. So building on that, a combination combination notation is very close to earlier. It's very close to permutation notation. But this time, instead of a P, we have C. So we have N, and instead of pick, we're going to say choose. And choose R represents the number of combinations of N objects chosen R at a time. So again, C for choosing. And here we choose them, and order doesn't matter. That's the difference between a combination and a permutation. So to calculate NCR, that's equal to n factorial all over r factorial times n minus r factorial. Cool? Again, C for combination. Let's do an example. So let's say in our algebra class we have 23 people and we want to come up with a leadership board. We want to say who our leaders going to be. How many different 4-people groups can we make? Well, that's going to be a combination. Because our combination, we're picking from 23 people, so that's going to be our n, because n is our total. And then 4 is going to be an r, because we are picking r number of objects. And by objects, I mean people. Oh, you guys aren't objects. Okay, so that means NCR is, let's see, our N is 23. It's going to be equal to 23, choose 4, almost wrote R again. And according to our formula, that's 4 factorial. Nope, just kidding, don't write that. It's 23 factorial all over 4 factorial times 23 minus 4 factorial. Now 23 factorial, we're not going to simplify quite yet to save on space. And then 4 factorial, 23 minus 4 is 19, so 4 factorial times 19 factorial. And then we could write that all out, or I can just calculate it in my calculator, and it comes out to 8,855. So there are almost 9,000 different options to pick 4 people from our class. Isn't that great? So great. Okay, now, but what if? What if? What if order did matter? What if we gave them positions? Like, positions, yeah. For example, instead of just picking 4 people, what if we assigned a president, and we assigned a vice president, a secretary, and we assigned a treasurer? Then order mattered. Because let's say we pick, let's say Will is a president, and then Riley is our vice president, and then Ryder is our secretary, and then finally Rachel is our treasurer. That would be different than if Ryder were our president, Will were the vice president, Riley were the secretary, and Rachel the treasurer. That's a different option. Or even if we just switch them around and make Riley the treasurer and Rachel the secretary. That's yet another different option. So if we gave those positions, that's no longer a combination. That would be a permutation because order matters. Here we would want to do NPR because order matters. So in a permutation is all about arranging them in different positions. You can remember like P for position even. And you guys, that comes out to 212,520 different options. So there's a lot more, right? That's like 2.5 times as many options if we gave them positions. Cool. Alrighty. So, the difference between a permutation and a combination is that in a permutation, order matters. And in a combination, order doesn't matter. Keeping those in mind, I have 3 situations for you. Determine whether or not we're going to want to use a permutation or a combination. For first one, if you want to figure out how many different ways you can pick 3 flowers to put in a bouquet from a selection of 15 flowers, would that be a combination or a permutation? That would be a combination. Because just combining them, there's no specific order that your flowers go in. You're just kind of putting them all in the same vase. So order doesn't matter. It's a combination. For a second one, how many ways to arrange the books on your shelf? Well, this one is going to be a permutation because arranging things, that's your key word here, arranging means a permutation because the order matters. You can order them alphabetically. You can sort them by color. You can sort them by size. You can sort them by genre. You can sort them by whether you've read them or not. Here you're putting them in order, so that's a permutation. And finally, how many combinations you can have on your locker. This is a trick question. It's a permutation. So even though it says combination, when you have your locker, order matters because there's a difference between, dialing a 438 and then 348. That's going to be the wrong combination. So when we say locker combination, we're actually using combination wrong. It should be a permutation. Why? Because in permutations, order matters. And in combinations, order doesn't matter. Okay. The key ideas from today, remember to write down these formula. They are super important. The combination formula and the permutation formula. In fact, if we put them together, this is one last thing I wanted you to see. Hold on, come back. Copy. Bring it down here. My paste. Here it is. So here's the formula for a permutation. And here's the formula for a combination. What do they have? Just kidding. No, come back. Nice. What do they have in common? Well, they both have an n factorial up on top. And they both have an n minus r factorial on bottom. But a combination is different because it has r factorial in the denominator. That's the only difference. So they look very, very similar. Again, permutation means order matters. Combination order doesn't matter. Keep these in mind. Love them forever. And I hope you have a great time on your homework.